This video is about arc length and the 1/2 trick. Recall that given a curve f that is continuous and differentiable on an interval a, b, the length of f of x from x equals a to x equals b is the integral from a to b of the square root of the quantity 1 plus f prime of x all squared dx. Most arc length integrals are notoriously difficult to evaluate. Since the square root of 1 plus f prime of x all squared is not equal to 1 plus f prime of x, we cannot split up the square root this way. So we end up with an integrand that is difficult to find an antiderivative of. For example, suppose we wanted to find the length of f on the interval 1 to 8, where f of x equals 10 times natural log of 3x plus 2. We take the derivative and we get 30 over 3x plus 2. We take 1 plus f prime of x all squared and we get 1 plus 900 over 3x plus 2 all squared. So the length of f of x from 1 to 8 is the integral from 1 to 8 of the square root of 1 plus 900 over 3x plus 2 all squared dx. This is a perfectly good integral, but how to evaluate it? This is a very challenging integral to evaluate. This brings us to what I like to call the 1/2 trick. Sometimes it happens that 1 plus f prime of x all squared can be rewritten as a perfect square, which is good because in the formula for arc length, it goes under a square root. If f prime of x has the form a minus b, where negative 2ab is equal to negative 1/2. Now what's special about negative 1/2 is that in the formula we have 1 plus, and so if we end up with negative 1/2 as our middle term, 1 minus 1/2 equals positive 1/2. So let's explore. 1 plus a minus b all squared. When we multiply out a minus b all squared, we get a squared minus 2ab plus b squared. If we know that negative 2ab is equal to negative 1/2, we can replace negative 2ab with negative 1/2. Then 1 minus 1/2 is positive 1/2. But positive 1/2 is equal to positive 2ab. And so we end up with a squared plus 2ab plus b squared, which refactors as a plus b all squared. So the square root of 1 plus a minus b all squared ends up being equal to the square root of a plus b all squared, which equals a plus b as long as negative 2ab is equal to negative 1/2. Now, technically, the square root of something squared is actually the absolute value of the something. But in practice, a plus b will often end up being positive anyway, and we won't have to worry about the absolute values. But just look out for that. Let's do an example. Find the length of the curve given by f of x equals 1 over 36x cubed plus 3 over x on the interval from 1 to 2. We need to take the derivative to use the arc length formula. We have f prime of x equals 1/12 x squared minus 3 over x squared, which is of the form a minus b. So let's check what will be the middle term when we multiply out a minus b all squared. 1/12 x squared, that's our a, and 3 over x squared is our b. So negative 2ab is equal to negative 2 times 1/12 x squared times 3 over x squared. which simplifies to negative 1/2. So the square root of 1 plus f prime of x all squared is equal to the square root of 1 plus a minus b all squared, which equals the square root of a plus b all squared, as we saw on the previous page. Now observe that a and b are both positive, since x squared is always positive on the interval of 1 to 2, and so a plus b is positive. And therefore we don't have to worry about absolute values in this step. So the square root undoes the squaring, and we end up with a plus b, which is 1/12 x squared plus 3 over x squared. This means our integrand is going to be easy to work with. The length of the curve is the integral from 1 to 2 of 1/12 x squared plus 3 over x squared dx. An antiderivative of this integrand is 1 over 36 x cubed minus 3 over x. Evaluate from 1 to 2, and you should get a final answer of 61 over 36. Here we come to a concept check. Pause and explore. I urge you to pause the video and work out the answer for yourself before continuing. Suppose f of x equals c times e to the 3x plus d times e to the negative 3x. Can you find values of c and d such that the middle term of f prime of x all squared is negative 1/2? Pause the video and come back when you're ready. Okay, so let's explore. When we take the derivative, c and d are just constants, so the derivative is going to be, using the chain rule, 3c e to the 3x minus 3d e to the negative 3x, which is of the form a minus b. And I have a typo here. I meant to say f prime of x all squared is of the form a squared minus 2ab plus b squared. So let's check the middle term. Negative 2ab equals negative 2 times 3c e to the 3x times 3d e to the negative 3x. And when we simplify, we get negative 18cd. So let's set this equal to negative 1/2. When we simplify again, we will see that cd must be equal to 1 over 36. So we have infinitely many choices for c and d, as long as they multiply together to give us 1 over 36. We could choose, for example, c and d are both 1/6. We could choose c equals 1 over 36 and d equals 1. Or vice versa, c could be 1 and d could be 1 over 36. We could even choose something more creative, like c could be the square root of 5 over 12 and d could be 1 over 3 root 5. In all of these examples, c times d is equal to 1 over 36. And that means the 1/2 trick will apply for any of these choices. So let's construct an example based on one of these choices. Let c be 1/4 and d be 1/9 for the previous problem. So that means f of x equals 1/4 e to the 3x plus 1/9 e to the negative 3x. Find the length of the graph of f on the interval from 0 to 1. I encourage you to pause the video and try to work out the answer for yourself on this problem as well before continuing. Okay, so the derivative is 3/4 e to the 3x minus 1/3 e to the negative 3x, which is of the form a minus b, with negative 2ab equals negative 1/2, because we worked that out in the previous problem. So we expect 1 plus f prime of x all squared to be equal to a plus b all squared. You can double check that 1 plus f prime of x all squared refactors as a perfect square 3/4 e to the 3x plus 1/3 e to the negative 3x all squared. Therefore, the length of f on the interval from 0 to 1 is the integral from 0 to 1 of 3/4 e to the 3x plus 1/3 e to the negative 3x dx. When we evaluate the integral, we get 1/4 e to the 3x minus 1/9 e to the negative 3x. Now you might be noticing that this antiderivative is very similar to the original function, except that there's a minus sign here where there was a plus sign. This is not a coincidence, because when we took our derivative in the first place to get our a minus b, if we think of the first term of f of x as being, say, g, and the second term as being h, then a is g prime, and our b is actually minus the derivative of h. So when we end up having to integrate a plus b, we're actually integrating g prime minus h prime, which is g minus h. So it's not a coincidence that we started with g plus h and wound up with g minus h as our antiderivative. To finish the problem, we just have to evaluate our antiderivative from 0 to 1. Plug in 1, plug in 0, subtract, and simplify, and we end up with e cubed over 4 minus 1 over 9e cubed minus 5 over 36. In summary, most arc-length integrals are difficult to evaluate, since in particular we cannot split up a square root by plus signs. If f is continuous and differentiable on an interval from u to v, I'm using u to v instead of a and b so as not to confuse it with the capital A and B in the 1/2 trick. If f is continuous and differentiable on the interval from u to v, and f prime of x is of the form a minus b, where a plus b is positive and negative 2ab equals negative 1/2, then 1 plus f prime of x all squared can be rewritten as a plus b all squared. So the length of f from u to v can be written as the integral from u to v of a plus b dx. I hope you found this video helpful.